Right, good evening, ladies and gentlemen. This is the last of our indoor meetings for the winter-spring season, and it's my pleasure, going to be my pleasure to introduce Dr. Chris Duffin, who's come all the way from London to speak to us this evening. Chris, his background, after his first geology degree in London, City of London Poly, I think you said, he then went to UCL to complete an MSc and then a PhD, where his main focus was on vertebrate paleontology. And he then went on to have an illustrious teaching career, teaching in, was it geology or geology and biology. And then finally, in more recent times, is Associate Research Fellow at the Natural History Museum in London. So anyway, tonight he's going to speak to us on the topic of diamonds. And I think I'll just leave it to Chris. Okay.
Thank you, Alan. And nice to be here. Thank you very much for the invitation. And I must say that it's nice to see a place that has two-tier seating, the front and the rear stalls. And it's always interesting to see who goes to the 1 and 9s at the back. And is that the place where the snoring comes from halfway through, or, well, you tell me. I think actually this is most appropriate to be talking about diamonds actually here, because as soon as I came past the sign for Dudley off the motorway, the first thing I saw was a blue number 14 bus with diamond written on the side. So I think that's a good omen. I was talking to Alan beforehand, and we both agreed that in our geology training, we had never, ever come across precious stones, which when you think of it is a bit daft. And the lecture that I'm giving you tonight has grown out of a WEA class, mostly, that I gave. And as you can tell, since I'm a vertebrate paleontologist, it's a bit outside my normal area. So, but if you look at any mineralogical textbook or internet entry summarizing the defining characteristics of any particular mineral, the pattern of information is always more or less the same. There's the position in the mineral classification scheme, the chemical composition, the crystallography, and then a list of other properties. Well, we'll start off this evening by just reviewing some of those. Next slide, please. So I'm going to have to keep digging, Alan. We should have had a cattle prod or something. This would have worked well. Well, the mineral classification scheme in current use is a hierarchical one, and it's based on chemical composition. It was first proposed by the German mineralogist Carl Hugo Strunz in 1940, and later edited versions appeared by the Canadian mineralogist Ernst Henry Nickel, leading it to being called the Nickel-Strunz classification. There are 9 mineral classes proposed, and each has a number of subclasses. And class number 1, next slide, is the native minerals. Native element minerals are those which are made up of single elements only, not combined with any others, and they possess a distinct mineral structure. Amongst these, diamonds fall into group 01C, the metalloids and non-metals, reflecting the position of the elements in the periodic table. Well, all of the native carbon minerals here have therefore got the same formula, just C. That'd you go in, Alan. Although they have the same formula, the structural arrangement of the carbon atoms differs. This means that they're called allotropes of carbon. Well, I expect, like me, there are a few here that you've never heard of. The existence of kaolite, for example, or white carbon, is rather disputed. It was found in the famous meteorite impact site at a place called Nördlingen-Ries in southern Germany. Slide. The town of Nördlingen, which unfortunately one presumes is the home of the nerds, is built in the depression of a meteoritic impact crater formed during the Miocene. And the locals exploit the impact breccia known as suevite as a building stone, and it's composed of rock and mineral fragments with glass bombs of crystalline basement melt mixed in. And it was deposited from the ejector plume that contains this mineral kaolite. And local buildings are sometimes claimed to be made as a result of diamonds. Of course you would. It's bound to put up the price, isn't it, in the local paper. Lonsdaleite is another very rare carbon mineral found in meteoritic debris. Next slide. In diamond, the carbon atoms form a three-dimensional structure in which every atom is bonded to 4 uniformly distributed neighbors. So as you can see here, we've got 1 carbon there, 1, 2, 3, 4 that it's joined onto. This is just like the arrangement of silicon atoms in framework silicates such as quartz. In graphite, though, on the left, you can see that each carbon shares bonds with only 3 other atoms. So, for example, that one there shares with 1, 2, 3 others. And instead of the 4th one, what we've got is them formed into a sheet, and it bonded to the sheet below by very weak forces known as van der Waals forces, which means that the sheets can slip past each other very easily. And this accounts for many of the dramatic differences that you've got in hardness and other characters between diamond and graphite. Well, how do we know that diamonds are actually carbonaceous? Next slide. I have to admit that I'm part of a generation whose schoolboy ideas of high literature was the next issue of Superman comics, because he's the superhero, of course, who could transform coal into diamonds by pressurizing them in his bare hands. How better to make a suitable gift for Lois Lane? Next slide. Although it was known more than a century earlier that diamond could be completely burned, leaving no residue, in 1772, Antoine Lavoisier, French chemist, sometimes known as the father of chemistry, and he repeated an experiment by placing a diamond in an oxygen-filled glass jar, and he heated it with focused light from the sun. And based on the production of carbon dioxide gas within the jar, he determined that the diamond was composed of carbon. And this result was later confirmed by 2 other people, Smithson Tennant in 1797 and Humphrey Davy in 1814. Next slide, we hope. Yes, well done. In 1797, James Smithson Tennant of Smithsonian Institution fame, and also Smithsonite, the minerals named after him, he reported the results of his experiments about the combustion of diamond and its composition. He heated powdered diamond with potassium nitrate in a gold tube and obtained carbon dioxide as the only product. Well, that was just the same as what Lavoisier had done. But Smithson Tennant's novel observation was that the volume of the CO2 released by burning the diamond was exactly the same as the volume of CO2 released from an equal mass of either charcoal or graphite. So this proved that diamond consists entirely, as he wrote, of charcoal, differing from the usual state of that substance only by its crystalline form. Well, now let's have a look at some other characteristics of diamond before considering a few of them in detail. Next slide. So we've got the color, the luster. Diamond gives its own name to a type of luster, of course, adamantine luster. Diaphaneity is how well it transmits light, and it is transparent. Crystal system is isometric, which we might commonly call cubic. Its habit is often in the form of cubes and octahedra, and famously it has a hardness of 10. Next slide. Specific gravity, 3.5, so it's a bit denser than quartz, which is 2.66. Cleavage, perfect cleavages, which of course helps when it comes to dressing diamonds ready for setting in jewellery and so on. Fracture is conchoidal, streak is white. It always makes me wonder how they measure the streak of a diamond, since not much, since it's basically the hardest material known, but experiments have been produced to do that. And it's associated with various minerals that we'll come across in kimberlites shortly, and it's found in various places, notably South Africa and Africa, India, Brazil, Russia, Australia, Arkansas, and so on. So if we, next slide please, if we go to the color of a diamond is affected by several factors, including contaminants in the crystal lattice, how they're arranged, and the amount of deformation and the presence of any inclusions that there are in the crystal lattice. So the most common type of impurity is nitrogen. Now you wouldn't think that would make much difference, but the volume and positions of the nitrogen atoms in the crystal lattice is what gives you an amazing range of colour, largely in the sort of pale yellow to brownish appearance, and it accounts for the type 1 type diamonds. Type 2 diamonds mostly have colour changes due to discontinuities in the crystal that result from very high pressure formation and no measurable nitrogen. So it's due to something completely different. And we see that in one of these particular groups, boron is a common impurity, which gives rise to bluey grey colours. So it's not just the sort of transparent whitish colour that you would normally expect to see. So we can see that this generally used classification system has got these various groups and subgroups. Next one, please. The Gemological Institute of America, GIA there at the bottom, has produced a colour grading system. And a set of diamonds of standard colour is used to compare other specimens to. And you can see that it's a highly precise system, because how do you tell the difference between reddish purple, purple red, purplish red, and red? I mean, they look very, very similar to me. It's very fine, slight difference of grade, but it can make all the difference to the price of the gemstone that you're looking for. And note as well how colour intensity changes as we go through the blues. That's basically due to the amount of boron that there is in the crystal lattice, as we said before. And there are also colour changes that are due perhaps sometimes to inclusions, such as the presence of tiny bits of graphite and that sort of thing caught up in the diamond. Next slide, please. Well, colour diamonds are usually referred, not surprisingly, to as fancy diamonds. And here are some of the most famous individual fancy diamonds, illustrating the colour range that you can get in this particular mineral, and we'll meet some of these in a bit more detail later on. Next slide. The mineral hardness scale was developed by Frederick Mohs in the early 1800s, and it's a relative qualitative scale, and one of the first things that you learn on any geological course, whether it's in the field or in the lab, is the hardness scale. In fact, if you go out in the field and somebody finds a mineral, you can usually find somebody muttering to themselves, "Tall girls can flirt and other queer things can do," working their way through the system of hardnesses and then fumbling in their pockets for bronze coins and their penknife to make sure that they can scratch it adequately. There is, however, a series of quantitative tests of hardness, and the most generally used is what's known as the Vickers hardness test, which is what we've got illustrated here on the vertical axis. And if it's plotted against the Mohs scale, look, all the minerals go in the same sequence, but whereas you get the impression here that it's just a straightforward 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, when you look at what's going on here with diamond, when you measure it quantitatively, it's actually 4 times harder than the next one, which is corundum. So this explains a little bit about the exploitation of diamonds for their hardness. Prior to the 1950s, low-grade diamond rough, as it was called, which was the sort of grit and the powder that was left over from diamond workings, those were used for machinery, for cutting, for drilling and grinding tools. But following the development of synthetic diamonds, natural sources were no longer required, and the uses of diamond began to expand further. And now they're used on many items that require resistance to scratching, abrasion, wear, and distortion under pressure. Next slide. One early means of exploiting this hardness was in scribbling rings, which were produced in late medieval and early modern times. They were exchanged between lovers, and these uncut diamonds were used to incise messages onto window glass. And Sir Walter Raleigh is believed to have written a message to Elizabeth I, "Fain would I rise, but that I fear to fall," to which she replied, "If thy heart fail, do not raise at all." And this example on the left is a scribbling ring from around 1430, and you can see that we've got a nice pointed, completely unworked diamond in the tip there. Now, as far as scratching and abrasion resistance is concerned, next slide, Rolls-Royce developed a diamond-based paint for custom-built examples of their Ghost sedan range in 2017. Just imagine keying that on your way home from the pub. It shouldn't work at all. Next slide, please. Also, diamond-coated lenses are commonly advertised for spectacles, for scratch resistance and all sorts of optical accessories, and it really is due to a coating of diamond on the surface. So mobile phones, camera lenses, spectacles, all those can have diamond-coated coverings on the top. Now, of course, machinery that can grind, cut or drill is important in all sorts of scenarios: agricultural, construction, automotive, manufacturing. And the use of diamond has the advantage that it can work at faster speeds for longer periods of time with more predictable wear patterns compared to other materials. It significantly increases the lifetimes of such equipment. Next slide. And a rapidly growing application is cutting wire for saws. Steel wire is coated in a resin that is impregnated with diamonds of different grade, powder size up to about 1 millimeter. And whereas traditional saws can only cut in one direction, diamond wire can cut rounded edges. So it's a bit like a coping saw in a way. You can change direction as you're using this, well, it's not a very fine one, but if you use a very fine one to cut out pieces of surgical equipment and computer parts and that sort of thing, then these resin-coated diamond impregnated blades are good. Next slide. Diamond crystallizes in the isometric or cubic system, giving a range of crystal forms that you're probably used to seeing in a range of other minerals. You probably recognize most of those shapes down the side there, typical garnet type crystal shape, pyritohedra, octahedra and cubes and so on. Next slide. And they also quite commonly twin on what's known as the Spinel law, and these are all examples. That's quite a good example of a twinned crystal, but you can see the way that what's happened is that a new crystal has grown along one of the crystallographic axes and penetrating the original. Next slide. So far we know that diamonds are single element minerals with occasional impurities. They crystallize in the cubic crystal system. They consist of closely packed atoms in a three-dimensional array, and that confers very high hardness on each crystal. So what are the conditions under which these minerals then form? Well, this is a fairly simplified phase diagram that starts to answer the question. The sheet-like arrangement of carbon atoms in graphite, which we've got down there, transform to the diamond lattice up there with increasing temperature and pressure on there and temperature on that axis. And this correlates, increasing temperature and pressure, with increasing depth of burial. The problem is that it doesn't increase evenly, and at different places over the Earth's surface, that increase, the sort of curve of that increase, it differs, but it's always got the same shape. So we've got this geotherm, as it's called, which is, or the geothermal gradient, the line which maps through the temperature increases with depth. And the point where that geotherm makes contact with the diamond graphite phase change there is the point at which diamonds begin to crystallize out. So what we need to know is, well, where in the Earth do you get those, or where on the Earth, you should say, where on Earth do you get those things changing? Where's the point in the body of the Earth where the geotherm crosses this phase boundary, the point at which most diamonds form? Next slide. Well, the primary sources of diamond are two very rare types of ultra-basic igneous rock. Names that you might have come across, but probably few of you handled rocks of this type, I would imagine. They're called kimberlite and lamproite. And we've got to notice that they have certain things in common, but lots of differences as well. Both of them are quite rich in magnesium, silica pore magnesium rich. Look, we've got magnesium rich there. They both occur in volcanic type situations, although this is more hypabyssal, which is below the surface type rocks, but you do get them as volcaniclastics as well. These form also in the superficial and hypabyssal range. We've got olivines of forsterite composition, that's magnesium rich olivines, and we've got lots and lots of chromium associated with kimberlites, which is much rarer in the lamproites. And we've got various other crystals as well, which characterize each. So there's certain similarities in terms of the place of their formation, their form, but their mineralogy and their bulk chemistry is slightly different. Well, diamonds have got high strength and low reactivity because of their framework structure. This means that any non-diamond material that gets caught up in the crystallization will form inclusions. And these might be solid mineral phases, things like little bits of garnet or oxides or sulfides, or commonly a silicate known as perovskite. Sometimes it's fluids, sometimes even gases in little tiny bubbles caught up in the diamond crystal. So the diamond is acting a bit like a capsule, enclosing these samples from the environment of formation and then bringing them to the surface. And the inclusions may predate the diamond. They might have been around and then the diamond sort of gobbled them up during crystallization. They might occur at the same time as the diamond crystal forms, or it may be that they're post-formation, something that's been caught up in the crystal and then changes afterwards inside its little capsule in the diamond material. The important thing is, though, that these inclusions have got a lot of potential for yielding information concerning the history of individual diamonds, that is, the depth and the context of their formation, and also their ages. Next slide, please. So just to remind you, because I'm aware that not everybody's necessarily really gone on geology, but the internal structure of the Earth, discovered largely through seismic waves, consists of an outer lithosphere, which is the outermost rocky shell, made up of the crust and the lithospheric mantle, which is the upper elastic layer of the mantle where convection currents don't take place. And this is underlain by the weaker asthenosphere where convection does take place. And that crust on the outside is of two types: basaltic oceanic crust and granitic continental crust. And these are arranged in a series of tectonic plates which are in constant relative motion. Oceanic crust may plunge beneath continental crust at subduction zones and or destructive plate boundaries, but it's renewed at mid-oceanic ridges or constructive plate boundaries. And continental plate cores here are made up of stable areas known as cratons. In the old days, they used to be called basement rocks. Next slide, please. Well, diamonds have got two distinct points of origin. Some originate in a zone with temperatures up to about 1300 degrees C in the cratonic lithosphere. So that's these ones over here. And others, sublithospheric ones or super deep ones, are rather deeper, down to perhaps 800 kilometers deep. How do we know this? Well, it's all to do with those diamond inclusions that I mentioned. But firstly, I've got to remind you about two further rather exotic rock types. Sorry about all this. Next slide, please. These are them, or will be them. We've got peridotite on the left and eclogite on the right. Peridotite is the rock type that is believed to make up the mantle. It's an ultramafic, that's high magnesium, low silicon rock, characterized by the presence of magnesium-rich olivines, as we saw there, and pyroxenes, mostly monoclinic and orthorhombic ones, and occasional garnets as well. Eclogite, on the other hand, is a metamorphic rock. It's rare at the Earth's surface. It does contain magnesium-rich garnets. The pyroxenes on this instance, though, are sodium-rich, which is rather different to the pyroxenes that we've got from peridotites. And it's formed by the metamorphism of subducted crust. So as a basaltic crust goes down beneath the continental plate at a subduction zone, bits of the crust break off and get highly metamorphosed and sometimes undergo complete melting. That's where you get the eclogite formed. These two rock types, therefore, come from two slightly different tectonic settings, and the detailed chemistry of the constituent minerals, especially the garnets and pyroxenes, differ. Next slide, please. So if we look at the mineral phases inside the diamond, so these are the diamonds, and these are other minerals caught up in there that the diamond is caught up from either the mantle or from below the continental crust and bringing to the surface. So basically we've got difference between the two. Some we've got olivine in, not likely over there. This is the peridotitic crust, which represents the mantle. The eclogitic crust material doesn't have that. We've both got garnets and we've both got pyroxenes, but we know there's a difference in chemistry of the pyroxenes in that those are sodium-rich ones, these are more magnesium-rich ones. So these inclusions fall basically into two groups. Diamonds that have got garnets and pyroxenes, which basically have a composition the same as eclogite, the stuff that's made down in the subduction zones, and others that have got garnets and pyroxenes that are peridotitic, which is more indicative of mantle composition. Next slide, please. So, oceanic crust subducted deep into the mantle undergoes partial melting. There's the subduction look. There's the crust going down, breaking up. It's undergoing partial melting. So diamonds that have already crystallized down here can get caught up in these rising mantle plumes that are coming towards the surface. So they've preformed, they get caught up in the rising magma, these plumes coming up through the cratonic material. And once they get to the base of the continental crust, they tend to get stuck. There's a slab which is called the mantle keel, which is basically the bottom part of the lithosphere stuck onto the underside of the continental crust, and there tends to be an accumulation of diamonds there which have come up from those lower depths. But also, if you notice, there's that line going through there. That's the phase change from graphite to diamond. So also, we've got, as soon as you get to temperatures that go from graphite to diamond, look, we get diamonds forming of their own accord in that region as well. So this region here gets contaminated with all sorts of things. Diamonds that are produced by growing because of the phase change, but also diamonds that are coming up from the lower mantle via the mantle plumes below. Then all it's got to do is punch its way to the surface and through appropriate volcanic rocks, which are the kimberlites and lamproites that I was talking about before. Now, the other interesting thing about these inclusions is that you can date them. Now, we're used to potassium argon dating and uranium lead and so on, but the very, very tiny amounts of inclusion material that get in diamond makes it very difficult to assay these materials accurately. And so a different decay sequence is commonly used, which has a very long, I can't honestly remember the name of the length of the half-life, but it's rhenium to osmium decay, which is most unusual. But it's quite useful because if you can date one inclusion in the diamond and another one, you've got a set of dates which suggests something of the history of that diamond as it's come up through and onto the surface. And so what we tend to see is that diamonds around this sort of area are often dated to up to around about 150 million years old. But diamonds that come up from down there can be anything up to 3.5 billion years old. And the interesting thing is that as the mantle plume comes up through here, of course, it might contain occasional nice large diamonds, old diamonds, 3,000 million years old, let's say, from down in the basal part of the mantle. But it's also picking up some other 150 million years old ones. So you get a mixture of diamonds, which is telling you something as well about the history of the plume and where it's coming from. It's all very clever stuff. So next comes the question of how do the diamonds get to the surface? Well, taking the case of most kimberlites, partial melting of the peridotite mantle produces, next slide please, magma in or around that transition layer, and the magma ascends through the continental cratonic crust, and on the way it collects diamonds, like we said, that might have crystallized in the ancient past in the mantle, plus potentially those of a mixture of ages stuck to the mantle keel, together with any entrained mantle xenoliths and xenocrysts and other rubbish that's coming up through. And the rising pluton feeds a series of dikes and sills in the country rock in the subsurface hyperbysal zone of the intrusion. And then rapid ascent occurs through pipe-like things called diatremes, which are these sort of carrot-like intrusions. And the high quantity of volatiles, that's carbon dioxide and water, results in explosive volcanic activity at the Earth's surface, producing various forms of pyroclastic landforms. Diamonds are found in other plate tectonic settings, but this is by far the most important, and that's illustrated in the next slide, in the distribution of productive diamond sites throughout the world. So now this is quite simplified, I have to say, but all these coloured bits are shield areas or cratons, those ancient cores of continental crust, and we can see that the major primary diamond-bearing things are all kimberlites, and they're in places here like South Africa, Namibia, Russia, and one in Canada, and we'll visit some of those as we go on the first time. So when it comes to mining, alluvial diamonds are the most recovered through screen washing of sediments, but kimberlite pipes like these are usually subject to open cast or underground mining techniques. But if we go back to the Middle Ages, the Iranian cosmographer and geographer Al-Qazwini, next slide, recommended an interesting approach. I'm sorry, I was a bit dense. He says this, he's writing in about 1280. Aristotle says that no one except Alexander ever reached the place where the diamond is produced. This is a valley connected with the land Hind, suggests he's talking about India. The glance cannot penetrate to its greatest depths, and serpents are found there. This is very deep, dark valleys, the like of which no man hath seen, and upon which no man can gaze without dying, of course. However, this power only endures as long as the serpents live, for when they die, the power leaves them. In this place, summer reigns for 6 months and winter for the same length of time. Now, Alexander ordered that an iron mirror should be brought and placed at the spot where the serpents dwelt. And when the serpents approached, their glance fell on their own image in the mirror, and this caused their death. It's all very Medusa-like, isn't it? Hereupon, Alexander wished to bring out the diamonds from the valley. Well, he would, but no one was willing to undertake this descent. Well, they wouldn't. Alexander therefore sought counsel of a wise man, and they told him to throw down a piece of flesh into the valley. This he did. The diamonds became attached to the flesh, and the birds of the air seized the flesh and bore it up out of the valley, and then Alexander ordered his people to pursue the birds and to pick up what fell from the flesh. Brilliant way of mining diamonds. You just send in the vultures after the serpents have died and then shoot them when they come back up because they got diamonds stuck to them. I don't know why we don't do that these days. So, next slide, please. Let's briefly consider a few examples of important diamond production centres with more traditional techniques of extraction. In 1866, Erasmus Jacobs found a small, brilliant pebble on the banks of the Orange River on a farm that he was renting. He showed the pebble to his father, and his father sold it. You just can't trust parents. It was a 21.25 carat, that's 4.25 grams, diamond, later known as the Eureka. 3 years later, in the same area, another gentleman, Schalt von Niekerk, bought another stone which had been collected there. This one was 47 carats from the farmer, and he bought it for the bargain price of 500 sheep, 10 oxen, and a horse. It was called the Star of South Africa. That's the diamond, not the horse. And he sold it for £11,200, and it was then resold in London markets for £25,000, and it's now in the Natural History Museum. Then in 1871, another diamond, 83.5 carats, this one, was found, and it was found by a cook. The cook had caught the ire of the owners of the farm that he was working, a group of brothers known as the De Beer brothers. And as a punishment, he was sent outside to dig holes. You know, the sort of thing that's not going to do anybody any good. And he found there an enormous 83.5 carat diamond. Within a month, 800 claims were cut into the hillock and were being worked by 2,000 to 3,000 men, and it became what is now the world-renowned Kimberley mine. So from mid-July 1871 to 1914, up to 50,000 miners were employed at any one time, hand-digging with picks and shovels, yielding a total of 2,720 kilograms, that's 6,000 pounds, of diamonds, and the pit was called the Big Hole. No wonder. The workings covered 42 acres, and the pit itself was enormous, 463 metres wide, excavated to a depth of 240 metres, then partly infilled with debris, and it's now got about 40 metres of water in it, as you can see. By 1873, Kimberley was the second largest town in South Africa. Not bad from a little hillock where nobody lived at all. Cecil Rhodes has the overall control of the Kimberley mine and eventually amalgamated with the De Beers. And once above ground operations became too dangerous and unproductive, the kimberlite pipe of the Kimberley mine, the first kimberlite ever identified, by the way, was mined underground by the De Beers and Cecil Rhodes Company to a depth of over 1,000 metres. Next slide, please. Up until the discovery of this particular kimberlite pipe, reworked diamonds had only been known from secondary deposits, especially alluvial deposits and occasional glacial tills. Canadian diamonds were the first found in glacial deposits and then traced back to the source area, which was that kimberlite pipe we identified in the map earlier on. Well, to continue the South Africa story, in May 1908, loose alluvial diamonds were first found in a beach sediment near the small town of Luderitsbucht in the former German colony of Southwest Africa, now Namibia. Over the next few years, rich diamond deposits were found along a narrow region of the Atlantic coastline. There we are. Southward from Luderitz Bay to the Orange River at Oranjemund. The diamonds could be recovered from ancient beach terraces that now lie inland, also on the modern beaches, or from the ocean bottom along the shore. And a land rush to this barren desert region then took place. Within 6 months of the discovery, the German government created a restricted diamond mining area that extended 100 kilometres inland and 320 kilometres along the coast. But after the defeat in World War I, South Africa took over administration of the colony, and the diamond mining area came eventually under the control of De Beers again, which it managed until the 1990s, I beg your pardon. And at that time, the Namibian government entered into a joint venture relationship with De Beers to recover and market the diamonds. And they're recovered, as we said, beneath beach sands along the coast, but also from a series of sediments dredged up by special ships from the seafloor and believed more recently from the Orange River. Well, these alluvial diamonds are thought to have originated from the primary kimberlite pipes within the high central plateau of the interior of South Africa, which is more than 300 miles to the east. Over some 80 million years of geological time, the diamonds were transported down to the Atlantic Ocean by the Orange and other river systems, and then carried northward along the coast by ocean currents to be deposited either on the bottom of the sea or along the coastline. And the extended distance of water transport tended to winnow out the poorer quality crystals, so the vast majority of the diamonds found in this remote coastal area here are actually suitable for gem quality use. Next slide. Well, in June 1955, Soviet geologists searching for kimberlites found surface traces of the rock type at Mir in Siberia, very close to the Arctic Circle. The development of the mine started in 1957 in extremely harsh climatic conditions. There were 7 months of winter per year that froze the ground, making it difficult to mine. And during the brief summer months, the ground began to turn to slush, so the buildings had to be raised on piles so that they wouldn't sink from the warmth of the melting permafrost. And the main processing plant had to be built on better ground 20 kilometres away from the mine. The winter temperatures were so low that car tyres and steel would shatter and oil would freeze solid. During the winter, workers used jet engines mounted on lorries like this to thaw and dig out the permafrost or blasted it with dynamite to get access to the underlying kimberlite. The entire mine had to be covered at night, would you believe, to protect the machinery and prevent it from freezing. In the 1960s, the mine was producing 10 million carats, 2,000 kilograms of diamonds a year, and a relatively high fraction, 20%, were high gem quality. The largest diamond of the mine was found in 1980, and it weighed 342 carats, that's 68 grams, and unfortunately, the mine is now worked and closed in 2004. Next slide, please. Another example is provided by the Argyle diamond mine in the Kimberley range of Western Australia. It's the first successful commercial diamond mine exploiting a volcanic pipe of olivine lamproite. And the volcanic pipe is the diatreme, that sort of carrot-like shaped thing that we saw before, composed of this rock, and we've got tuff and lava at the surface. And what we've got is a set of peripheral volcanic facies that suggest lamproite eruption forming a maar. Now, this is a modern-day maar. We've got a volcanic plume there, a fairly small crater, and a tuff ring around the outside, because this type of explosive eruption is called a phreatovolcanic eruption, and it takes place when usually groundwater, but any sort of water, comes into contact with the magma. And so you get a sort of a blast of material, and this is a sort of a more ancient maar. This is the tuff ring around the outside of a fairly recent one. Next slide, please. So this is the Argyll diamond mine, and the diamonds are found in the intact core of the volcanic pipe, as well as within some of the marginal breccias and maar facies material. The diamonds found here have been dated to about 1.58 billion years of age, but the volcano creating the pipe is only 1.1 billion years of age, so the diamonds are that much older than the volcanicity. And the average size of these diamonds and the unusual physical characteristics are quite important here. This is the world's main source of pink diamonds, which you can see here. And Argyll was at one time the largest diamond producer in the world by volume. It produced 14 million carats in 2018, but the proportion of gem quality material is quite low. Well, in addition to the pipe itself, a number of semi-permanent streams have eroded away portions of the pipe and creating significant alluvial deposits which were worked as well. And again, the Argyll mine is now defunct. It closed in 2020. Next slide. Probably the most famous source of alluvial diamonds is Golconda in eastern India. For 2,000 years, these diamonds were the only known fine quality gem diamonds that you could get. And due to centuries of excessive mining, their production was exhausted by 1830. The Golconda diamond industry was at its peak during the 16th to the 18th century, when 23 mines, of which Kollur mine was the most active, operated in the region, and 30,000 people at a time worked in one mine. The output from all the mines in Golconda is estimated to be around 10 million carats. That's about 2 tons. Next slide. And these Golconda diamonds were mined, as I said, from alluvial soils along the riverbed. They were washed out of clusters of kimberlite pipes that are now discovered in the Peninsular Shield in southeast India, and the finds include many famous examples, including the Kohinoor diamond, the Hope diamond, the Tavernier blue, the Daraya Noor. These are all, the Wittelsbach, these are all famous diamonds from the Renaissance period. Next slide. Well, having looked rather cursorily at the geological occurrences of diamonds, let's move on to its status as a gemstone. So the Gemological Institute of America proposed this 4 C's means of identifying quality in diamonds. There's the carat, or the weight, the color, which we've heard about, the clarity, a measurement of the number of flaws there are, and the cut. The cut is quite important because that can turn a fairly rubbishy diamond into a beautiful gem piece. Next slide. Now, you probably know from the Antiques Roadshow that gem quality is assessed on those 4 C's, and as far as carats are concerned, historically, carob seeds, that's the seeds of this tree, were used to measure weights in jewellery because it was believed that there was very little variance in their mass distribution. This is not actually true. They vary just as much as any other seeds, but they were so small that the amount of variance meant to say that there was comparatively little variation from the mean. So this has now been replaced, rather unfortunately, I rather like the idea of measuring in seeds, has been replaced by an international standard set at 200 milligrams. That's a carat. Well, we've already considered the colours of diamonds, but just to remind you, next please, the coloured diamonds, if you remember, have got nitrogen as the most common impurity. We've got boron giving blues and greys. We've got various deformations, and we've got inclusions in there. Next slide. Well, diamond clarity refers to the number and location of natural inclusions and blemishes. So you can see as we go along this sequence here, we got rather more and more and more inclusions, so that the diamond is becoming progressively lower clarity. And as far as colour is concerned, if you start off with a white diamond, the increasing amount of yellow, unless you're actually after a yellow diamond, means to say that this is getting poorer and poorer in quality as you go to the right. Next slide. What you do is you look at the diamond under 10 times magnification, so the normal loupe that you would use in the field. The higher the clarity grade, the fewer the imperfections, and that means to say the greater the brilliance, as it's called, and the value. Clarity is graded on a scale from flawless to included, and the brilliance is a measure of the amount of light returning to the surface of the eye. It's the white light reflected off of a diamond. It's one of the optical properties that reflects its beauty and its value, and by extension, of course, its price. A diamond's brilliance also forms the basis of its sparkle, as it's called, and its brightness. Diamonds don't naturally produce light or sparkle brightly. The sparkle results from the cut. And as you can see from these diagrams here, as light enters, if we have a shallow cut, much of the light is lost through the walls. If we have an ideal cut, then most of the light is returned to the eye. If we have a very deep cut, we've got the same sort of problems we've got here, we're losing light to the side. So this is the best situation, a certain amount of depth, best quality cut, return the most light to the eye so that you've got best possible sparkle, brilliance, fire, scintillation, everything. Next, please. So the cut of a diamond is important, and there has been something of an evolution of this characteristic over time. So firstly, let's look at the parts of the diamond. That bit that sits down in the middle of the ring itself, is with a point at the bottom, the culae, is called the pavilion. There's a girdle around the side, and then the top of the diamond is the crown. And at the top, we've got a table which consists of the different sorts of cut that you can have. Next slide. This is a very quick overview of the main types of cut. So this one's called a point cut, which basically has not been cut at all. It's just a basic octahedron. This one's had the top cut off look, so that we've got a square base at there. This one's got an added complication in that we've got chamfers down the sides there, and then we get progressively more and more complicated as you go through. Next slide. So we'll go through these very, very quickly, I think. So these are point cut diamonds, and you can see there, this is an example. There's the point cut. It's just like that scribbling ring that we saw before that Walter Raleigh was writing messages to Elizabeth I with. Cut the top off and you've got a table cut, and there we are, there's the squared top. Next slide. Adding a complication, we cut the edges off so that we've got what's called old single and pavilion cut, so that we end up with an 8 faceted pavilion around the outside. Next, please. Here we're making life more and more complicated. You can see the way that it's developing. Look, we've got extra cuts on the side, and this is the way that the pavilion looks. And depending on whether you shape the diamond or not, you've got a pavilion or a briolette cut. Next, please. And this one, the old mine cut, look, we've got two sets of cuts, top and bottom there. Much more complex around the crown, as you can see. Thank you. Next one. The old European cut, getting more and more complicated all the time. You can look this up online if you're interested. We're just looking to see the evolution of the things. Next. The modern cut, the brilliant cut that Geoffrey Munn gets excited about on the Activities Roadshow, which is where we've got most of the light returning to the eye. So next slide. This is a series of examples of those things. If you click, I think we get some explanations. So we've got the point cut. The table cut, just cut off the top look. Single cut, a bit more off the edges. The rose cut, which is where we've got 2 levels of chamfering. More complex down at the bottom of the pavilion. And the modern brilliant cut, which you can see is sparkling away there. Thank you. Next one. Let's have a look at some of the world's most spectacular examples of gem quality diamonds. In number 10, there's the Millennium Star, only 203 carats, owned by De Beers, and it comes from Zaire, insured for 100 million, but if it was stolen, who knows what they'd pay out. Next. There's the Red Cross diamond next, I hope. Yes, it is, and this is a slightly yellowish one. Look, we've got a Maltese cross on the top face, which gives it its name, came from Kimberley, and valued at 2 million. Next. The De Beers diamond, named after them. This is much better. You could identify the cut there for me, I think. When I pause like that, it's your turn. It's brilliant cut, brilliant cut. Kimberley again, 234 carats. Next. Jubilee diagram. This came from an original stone of 650, but once worked down, only down to 245. And again, from South Africa, named because of Queen Victoria's Jubilee in 1897. Next. The centenary diamond, discovered recently, 1986, 273 carats, again from an enormous original stone, and this one has got 247 facets in it. 100 million insurance in 1991. Next. The Spirit of Grisogno, we've got the largest cut black diamond, West Central Africa again, 587 carats before it was cut, and it's been set in this nice white ring. Next. The Cullinan. So this was found in 1905 in South Africa, the largest gem quality diamond ever found, but they went and cut it. It was, look, 621 grams, enormous for a diamond, 10.5 inches long, named after Sir Thomas Cullinan, but then they split it and cut it into 7 major stones and 96 smaller ones. And Edward VII had the Cullinan 1 and 2, the 2 big ones, set in the scepter and the imperial state crown. Next. And here's the original Cullinan diamond. Here's some of the larger bits. Next, please. And here they are, Cullinan, hang on, which one was which? That's Cullinan 1, and there's Cullinan 2 there in the crown. Next one, please. The incomparable diamond, 407 carats, 1984. She was going through some tailings of a diamond mine and found this in the Congo, and it's the largest brown diamond ever found. Next, please. The Cullinan 1, the Star of Africa that we've mentioned before in the scepter. Next. And biggest and best, the Golden Jubilee diamond, 545 carats, the largest faceted diamond in the world, again, or South Africa. Perhaps I should also mention, next one, the Hope diamond, because this is particularly famous, now housed in the Smithsonian. It was supposedly stolen from the eye of a sculpted statue of the goddess Sita, the wife of Rama, the 7th avatar of Vishnu, and therefore cursed. The original 115-carat stone was brought to Europe by the French traveller Jean-Baptiste Tavernier, and it was sold to Louis XIV in 1669. Here it was cut in 1678, the largest piece being the 67-carat stone that we've got here, and Louis had it set in a cravat pin. I mean, that would hold it in place, something that big. In 1749, Louis XV had it set in a jewelled pendant for the Order of the Golden Fleece, and then in 1792, during the French Revolution, Louis XVI was under confinement, and thieves stole the jewels from the royal storehouse. Many of the jewels were recovered, but the Order of the Golden Fleece and the Hope diamond was not among them. But in 1812, it appeared in the inventory of a London diamond merchant, and by 1839 it was acquired by Henry Philip Hope, after whom it's named, and after a series of sales in the 1900s was eventually sold by Cartier in 1910 to a socialite, Evelyn Walsh McLean, who sold it to settle her gambling debts in 1949. And in 1958 it was donated to the Smithsonian. Next, please. Synthetic diamonds were first produced in 1970 and are now big business, both for industrial grade and gem quality diamonds. HPHT, that's high pressure, high temperature diamonds. They're lab grown using, as it says, high pressure, high temperature, basically mimicking the natural diamond formation process in the mantle. It's the sort of Superman in captivity type production of diamonds. A small diamond seed is placed in a press surrounded by carbon and a metallic flux, and you press the button and hey presto, out come these diamonds. The CVD diamonds, that is lab-grown diamonds using a process known as chemical vapor deposition, it replicates the natural formation of certain types of diamond. A diamond seed crystal is inserted into a carbon-rich gas in a high-temperature environment, and sublimation onto the surface creates these diamonds. Identical to diamonds in all respect. Next, please. Synthetic diamonds offered a more ethical, environmental friendly alternative to mined diamonds, of course, and are also typically more affordable than natural diamonds of comparable size and quality. But when it comes to diamonds in popular culture, I dare say most of you would point to Marilyn Monroe singing "Diamonds Are a Girl's Best Friend" in the 1953 film Gentlemen Preferred Blondes. Next. Then there's Dame Shirley Bassey belting out "Diamonds Are Forever," which we now know is quite close to the truth because they're 3.5 billion years old from the lower mantle. That's the 1971 Bond film with the same name. Next. Going back a little further, there was one of Mae West's famous aphorisms in reply to a cloakroom attendant's comment on the beautiful diamonds she was wearing. Goodness had nothing to do with those diamonds, she said. The more cultured of you will, I'm sure, never thought of Mae West, but your thoughts will have certainly gone straight to Shakespeare, because I can tell you're an educated bunch. Next slide, please. I won't bother reading through these, but these are all the places that Shakespeare refers to or uses diamond as a standard. Next. And these three just from Pericles on its own. Next, please. Well, Hindu culture has always held diamonds in high esteem. They've been recovered from many Indian temple vaults where treasures are buried with the dead, and this most popular gemstone amongst all others play a significant social role in ancient Hindu culture. The word for diamond in Sanskrit is Vajra, the sacred language of Hinduism, and they were used as the eyes in sculptures of deities, indicating how highly valued they were to the ancient culture. And a common belief was that diamonds attracted lightning, and when lightning bolts struck a rock, diamonds were formed. And the Hindu scriptures believe there were 8 different types of diamond, each having its own colour, as you can see there. I won't bother trying to pronounce them. And it put importance on when to purchase a diamond. It had to be on a specific day, at a specific time, and even today many Hindus will only purchase a diamond on the Friday when the planet Venus lies in the zodiac sign of Taurus, Libra, or Pisces. Ancient Hindu culture put importance on when to purchase this diamond, and as we said, it had to be quite specific. And ancient Hindu physicians believed diamonds had power as well. They could cure illnesses, anything from fevers to problems with digestion, and so on. Next slide, please. Well, according to many ancient Indian religions, including Hinduism, the Asuras were a race of ancient demigods. There they are from Angkor Thom. A Vedic text known as the Garuda Purana explains the origin of gemstones. A demon named Vala conquered the god Indra and his associated demigods and reigned supreme and invincible in the universe. But the gods, on the occasion of a religious sacrifice, jokingly asked him to play the part of a sacrificial animal. So Vala consented to play the role as the animal and pledged his word to be bound at the sacrificial stake. The gods turned the jest into earnest and killed the invincible Vala in a mockery of the religious sacrifice. So Vala yielded up his ghost for the good of the universe and for the welfare of the gods. His severed limbs and the members of his sanctified body were converted into the seeds of gems. Next slide. The gods and demigods rushed eagerly to collect those gem seeds, and as they were being carried away, some of the seeds dropped to earth, and wherever they fell, oceans, rivers, mountains, wildernesses, those places became the origins of the mines through the celestial potency of the respected seeds. So drops of Vala's blood became rubies, his skin became yellow sapphires, he clearly suffered from jaundice, his eyes blue sapphires, and his bones shattered and became diamonds. Vala's teeth fell into the oceans and landed on oysters, where they became pearls, and his intestines were also thrown into the sea and became coral. His ruddy fingernails turned into hessonite garnets, and his toenails became the seeds of red pyrope garnet, which you might find in eclogite. His bright green bile became emeralds, and his fat turned into jade, while his semen became quartz. The rosiness in his complexion became bloodstones, and finally, even his last war cry that echoed around the heavens as he was killed was transformed into a cat's eye. Excuse me. Next. Ancient Greeks believed that diamonds were we're near the end now, don't worry, were the tears of the gods or broken splinters from fallen stars, imbued with divine power and celestial origin. They were seen as gifts from the heavens, connecting mortals to the divine realm. And diamonds were also thought to symbolize purity, love, and protection. They appear in a number of different Greek myths, and in one, the god Zeus transforms some children into things called adamastos, which actually gives us two words, diamond and adamantine. And you can see that term and its derivatives are being used throughout mythology. Next, please. Adamas and its brother Adamant, yes, I know, are used throughout mythology to further the connection to diamonds. Cronus castrated Uranus, his father, with an adamant or a diamond sickle, as you can see here, that was given to him by Gaia, his mother. And this same type of instrument is later used by the hero Perseus to decapitate Medusa as she sleeps. And the classic Greek philosopher Plato suggested that diamonds were actually living celestial spirits embodied in stones, further adding to the mystique and power that surrounded the stones. And there are all sorts of additional lore attached to diamonds. Next, please. One text says that you can purify them by dipping them in nightshade juice, place them overnight in a fire of burning cow dung, and in the morning place it in cow urine, burn it a second time, repeat the process for 7 days, and you'll get rid of all the inclusions. Magic. Next, please. What about these? In folk medicine, they were believed to bring the victory to the wearer. Marbode of Rennes in the 13th century said it's a magic stone of great power, driving away nocturnal spectres, and should be set in gold and worn on the left arm. Hildegard of Bingen from the 11th century says that the sovereign virtue was recognized by the devil. When he looked on these precious stones, he saw that it was perfection there, and therefore diamond is a great enemy to him because it resists his power by day and night. Next, please. Royus in the 1500s called it a gem of reconciliation because it enhances the love of a husband for his wife, as you would know, having been given diamonds upon diamonds throughout your married career. Cardanus, what's he, that's 1500s again, from Italy, is believed to make the wearer unhappy, he says. Its effect, therefore, the same upon the mind as that of the sun on the eye, for the latter rather dims and strengthens the sight. Indeed, it renders fearness. There is nothing that contributes to our safety than prudence and fear. Therefore, it's better to fear. He is a miserable character, Cardanus. And John Mandeville from, this is now 12th century, it happens often that the good diamond loses its virtue by sin and for incontinence of him who bears it. So you who've got diamond rings, be careful, because if there's any hanky-panky going on, your diamond is liable to lose its virtue. Next and almost final slide, please. There was also a belief that diamond was a virulent poison. Benvenuto Cellini, the famous Italian goldsmith, recounted an attempt on his life where an enemy supposedly ordered diamond powder to be mixed in his salad. However, the lapidary responsible for grinding the diamond instead substituted powdered glass for it, and Cellini survived. In 1532, Pope Clement VII was reportedly dosed with pulverized gems, including diamond, in his medication. And while this resulted in his death, the cause is more likely attributed to other factors rather than the diamond. And finally, Catherine de' Medici, another historical figure, was also rumoured to have used diamond powder for poisoning, further solidifying that misconception. So this evening we've seen something of the mineralogy, the petrology, the geological occurrence, and the folklore and traditions surrounding the diamond. So I hope there's been something in there for each one of you. Thank you.
A little anecdote I'd like to tell before I say proper thanks to Chris. I did many years ago work in a gem testing laboratory in London, and it was our job to test gems for some of the most prestigious places, and we had a gem in from Sotheby's, and it was a green diamond, and we reported on it, did our usual tests on it, and I wrote the report myself, and I sent it back to them saying that it was actually an irradiated diamond. And what did that mean? It was the case that in the 1930s it became very popular to have these green diamonds, and they made them green by putting them alongside radium for a while. The only trouble was that the diamonds then became radioactive, and a lot of the people that wore it developed problems. And I got the phone call back from Sotheby's, the person saying, "What does this mean that it's an irradiated diamond?" And I explained this, and I said that the fact that it's irradiated means that it's highly radioactive, and lots of the women that wore these diamonds developed cancers on their finger. And then he said, "Oh, did you hear that?" And I said, "What?" He said, "I just dropped it." Anyway, I'd like to thank Chris for giving us such a fascinating, informative talk about diamonds. I learned a massive amount about diamonds that I'd never heard before, and I'm sure that you found it equally fascinating. And I'd really just like you all to thank Chris for coming along all this distance to give us this talk this evening. So thank you.